Hello everyone! In this tutorial, we explain how to convert decimal to binary numbers. We will derive a general procedure for performing this conversion, and then we will solve several problems and examples. Okay, let's first briefly revise binary and decimal numbers. In computer engineering or computer science books, you will often see this notation for binary numbers. For example, you'll see 1, 0, 1, 1, 1, and over here you will see a base. This is one way of representing binary numbers. Binary numbers have the base of 2. Another way of representing binary numbers is to simply leave out the base of 2 and just to write 1 or 1, 1, 1. Let's explain what are the coefficients. The coefficients can be 1 or 0 in the case of binary numbers. And this coefficient over here is A4. This coefficient over here is A3. This coefficient over here is A2. This coefficient over here is A1, and this coefficient is A0. As mentioned previously, binary numbers are represented by using the base of 2. What does this thing mean? Well, this means that when we convert binary numbers to decimal numbers, we will multiply the coefficients of the binary representation by the corresponding powers of the base. In this case, base is 2. Consequently, the decimal representation of the binary number is obtained like this. We take A4 coefficient and we multiply A4 by 2 to the power 4. Then we take A3 coefficient and we multiply A3 to the 2 to the power 3. Then we take A2 coefficient and we multiply A2 to the 2 to the power 2. Then we take A1 coefficient and we multiply it by 2. Then we take A0 coefficient and multiply A0 to 2 to the power 0. Let us now substitute the values. Over here we have 1 multiplying 2 to the power 4 plus 0 multiplying 2 to the power 3 plus 1 multiplying 2 to the power 2 plus 1 multiplying 2 to the power 1 plus 1 multiplying 2 to the power 0. And let's calculate this. Over here we will have 16. Over here we will have 0 multiplying 8. Over here we will have 4. Over here we will have 2. And over here we will have simply 1. And if we compute this, we will obtain 16 plus 4 is 20, plus 2 is 22, and plus 1 is 23. Consequently, the decimal representation of our binary number is given over here. As we have seen previously, transformation from a binary number to a decimal number is straightforward. However, transformation from a decimal to binary number is not so trivial. In the sequel, we will derive a general procedure for transforming decimal number to any other number in any other base. As a special case, for base x is equal to 2, we will obtain the transformation from a decimal to a binary number. So let's introduce a new notation. We will represent a decimal number by a capital N. Lowercase x will represent the base. For example, in the case of a binary number, the base is 2. Then we will write this. Over here we have a decimal number n, and on the right hand side of this equation we have the representation of this number in the base of x. As we have seen previously on the example of a binary number, this representation is calculated by finding these coefficients an, an minus 1, an minus 2 until a0. If we follow the general rule, we will represent this number over here in the base of x as a decimal number by taking the coefficients and by multiplying the coefficients by the corresponding powers of x. And this is how we go from a binary to a decimal. So here is now a problem. Given a decimal number n, that is given n, calculate the coefficients an minus 1, an minus 2, a1 and a0 of its representation in the base of x. And this is the problem that we need to address. Before we explain the general procedure, let us first briefly revise the concepts of quotient and remainder. Let's say that we want to divide 41 by 2. We can represent this division like this. In the numerator, we will have 20 multiplied by 2 plus 1, and in the denominator we have 2. Now, 20 multiplying 2 divided by 2 is equal to 20, and over here we are left with 1 over 2. The integer quotient in this case is 20, remainder is 1, and 1 over 2 is the fractional remainder. Let's derive the general procedure. We start from this expression. The idea over here is to divide both the left-hand side and the right-hand sides of this expression by x. As the result, that is, as the remainder of this operation, we will obtain a0. So let's do that. Now, if I divide n by x, on the right-hand side, I will have an x to the power n minus 1 plus an minus 1 x to the power n minus 2, and then I will have an minus 2 x to the power n minus 3. Then over here, I will have a3 x to the power 2 plus a2 x plus a1, and over here I will have this expression a0 divided by x. The integer quotient is this part over here. And let's denote this part simply by q1. The remainder of this operation is a0. And this is how we get the first coefficient. Next, we perform this division recursively. That is, instead of n, now we take the quotient q1 and we divide the quotient by x. And as the result, we obtain q1 divided by x is equal to an x to the power n minus 2 plus an minus 2 x to the power n minus 3 plus an minus 2 x to the power n minus 4. And then if we sum all the terms, we will have a3 x plus a2 multiplying nothing, or better to say multiplying 1, plus a1 divided by x. That is, we see that if we divide q1 by x, we will obtain a new integer quotient, which is this part over here, and the remainder of this operation is actually a1. And this is how we obtain a1. Over here we obtain a0. Then we repeat this procedure again recursively. This part is now q2, and then we say again q2 divided by x is an x n minus 3 plus an minus 2 x n minus 4, and then we sum the terms. Over here we will have a3 plus a2 divided by x. Over here, this part will be a new integer quotient, which we denote by q3 And over here, the remainder is our coefficient, a2. And that's the general procedure. We repeat this operation recursively until we come at the coefficient a2. In the sequel, let's explain this procedure by using several examples. To illustrate the explained procedure, we consider this problem. Our problem is to represent the decimal number 41 in the binary base, that is, in the base of 2. For that purpose, we need to construct this table. The second column of this table will represent the quotient. The third column represents the remainder, and the last column will represent the derived coefficient. So let's start. We start with the number 41. We divide 41 by 2. This division can be represented like this. We have 20 multiplying 2 plus 1 divided by 2. From here, we can see that the quotient is 20. So we write it here. The remainder is 1, and the fractional remainder is 1 over 2. From here, we can see that coefficient is 1, since in the derived procedure, the coefficient is the remainder of the division, and it should be the integer remainder. We also have the fractional remainder, which we don't use. Consequently, over here, we have that a0 is 1. Okay, so this is the first row. Next, we repeat this procedure recursively. Now we take the quotient and we divide it by 2. The result is, first of all, we can represent this expression as 10 multiplying the base plus 0 divided by 2. And from here we can see that the quotient is 10, remainder is 0, and from here we get that a1 is 0. Good. Let's repeat this procedure. We take the quotient, we have 10 divided by 2, and this is equal to, let's see, we have 5 multiplying 2 plus 0 divided by 2. And from here we see that the quotient is 5, remainder is obviously 0, and we have our coefficient a2 is equal to 0. Good. Let's repeat this procedure a few more times. Now we take the quotient, it's 5. We divide the quotient by the base. We have, this is equal to, let's see, 2 multiplying the base 2 plus 1 divided by 2. From here we can see that the quotient is 2, remainder is 1, and we get the coefficient a3 is equal to 1. Next, let's repeat this procedure. We have, now we take the quotient 2, we divide 2 by the base 2, and we can express this as 1 multiplying 2 plus 0 divided by 2. From here we get that the quotient is, watch out here, the quotient is 1. Remainder is obviously 0. And from here we get that a4 is 0. Now we are not done. We still have one more coefficient. Why is that? Because we repeat the procedure until the quotient becomes 0. So over here we will have 1 divided by the base 2, and let's see what do we have over here. We can represent this as 0 multiplying the base plus 1 and everything divided by 2. And from here we can see that the quotient is 0, remainder is 1, and finally a5 is 1. And that's it. We end this procedure since we arrive at the quotient 0, and now our number is simply obtained like this. We take these coefficients and we go from down to up. That is, we go this way, and our number is 1, 0, 1, 0, 0, 1. And that's it. Let's double check our computations. Let's represent the derived number as a decimal number. We have this coefficient is a5. Consequently, we have 1 multiplying 2 to the power 5 plus 0 multiplying 2 to the power 4 plus 1 multiplying 2 to the power 3 plus 0 multiplying 2 to the power 2 plus 0 multiplying 2 to the power 1 and plus 1 multiplying 2 to the power 0. Let's see what do we have over here. 2 to the power 5 is 2 to the power 4 multiplying 2, and that's 32. Then over here we have 0. Then over here we obviously have 8. Then over here we have 0. Then over here we have 0. And finally over here we have 1. And the result is 32 plus 8 is 40, plus 1 is actually 41. And this is correct. The next problem is to represent the decimal number 53 as a binary number. So let's start. We start from 53 and we divide 53 with the base of 2. And this division can be represented like this. We will have 26 multiplying 2 plus 1 divided by 2. Over here we can see that the quotient is 26 and remainder is 1. Consequently, a0 is 1. Then, this is the first row. Next, we take the quotient and we divide the quotient again by the base of 2. And as the result we obtain. This division can be represented like this. 13 multiplying by 2 plus 0 divided by 2. Consequently, the quotient is 13, the remainder is 0, and the coefficient a1 is 0. And that's the second row. Let's continue. Next, we take the quotient, in our case it's 13, we divide the quotient by 2, and this division can be represented like this. We have 6 multiplying 2 plus 1, everything divided by 2. From here we can see that the quotient is 6, the remainder is 1, and the coefficient a2 is equal to 1. Let's continue. Next we take the quotient is 6. 6 divided by 2 can be represented as 3 multiplying 2 plus 0 divided by 2. Over here we can see that the quotient is 3, the remainder is 0, and over here we can have that a3 is equal to 0. Let's continue. Then the quotient is 3. 3 divided by 2 can be represented as, let's see, over here we can write 2 multiplying 1 plus 1, everything divided by 2. From here we can see that the quotient is, actually, here you have to be very careful about the quotient. Over here the quotient is actually 1, and this is very important. And the remainder over here is obviously 1, and consequently A4 is 1. And let's obtain the final row. Let's see. Over here the quotient is 1. 1 divided by 2 is equal to, let's see, that's 0 multiplying 2 plus 1, everything divided by 2. From here we can see that the quotient is obviously 0, remainder is 1, and the coefficient A5 is equal to 1. And that's it. We completed the procedure since the quotient is 0. And finally, our number is obtained by taking all the coefficients and going from down to up. And let's see, what do we have over here? We have 1, 1, 0, 1, 0, 1. And that's the final answer. Let us double check this procedure. We have our number, which looks like this: 1, 1, 0, 1, 0, 1, and everything is in the base of 2. Let's expand this number. The coefficient over here is A5, so let's type 1 multiplying 2 to the power 5 plus 1 multiplying 2 to the power 4 plus 0 from this coefficient multiplying 2 to the power 3 plus 1 from this coefficient multiplying 2 to the power 2 plus 0 from this coefficient multiplying 2 to the power 1 plus 1 from this coefficient over here. And let's calculate what do we have over here. We have 32 over here, then here we have 16, over here we have 0, over here we have 4, over here we have 0, and finally over here we have 1. Let's sum everything together. 32 plus 16 is obviously 48. 48 plus 4 is 52, and plus 1 is 53. And that's precisely the decimal number we had at the beginning. Okay, that's all for today, and thanks for watching.